You might remember from Calculus 1 we had what's called the sandwich theorem for functions. So we also have a similar theorem for sequences. So let's suppose you have three sequences, a sub n, b sub n, and c sub n. And let's assume that b sub n is always between a sub n and c sub n for every value of n. So in other words, every term of b sub n, so b1 would be between a1 and c1, b2 would be between a2 and c2, and so forth. Okay, so if that's true, then we know that if the limit of a sub n is L and the limit of c sub n is L, then the limit of b sub n must also be squeezed to that same limit L, of course, as n goes to infinity. Okay, so let's take a look at an example of that. Okay, so let's suppose you needed to find the limit of the sequence cosine squared n over 3 to the n, okay, as n goes to infinity. Well, first of all, we know that cosine of a value lies between 0 and 1. So therefore, since it lies between 0 and 1, I can't think now. Okay, so if you squared 0 or 1, you can't get a number bigger than 0 or 1. So basically, we know that the cosine squared of n lies between 0 and 1. So if that's true, if I were to divide this by 3 over 3 to the n power, and then divide this by 3 to the n power, because 3 to the n is a positive number, and then divide this side by 3 to the n power, then I would get this inequality. So basically what I've done is I've trapped the sequence here between two other sequences. Now one sequence is not a very exciting sequence, it's just 0, so that would just be 0, 0, 0, 0. So the limit of 0 is just going to go to 0 because all the terms are going to be 0. But here the limit of 1 over 3 to the n, this particular sequence, it goes to 0 because the top remains constant and the denominator increases without bound, so this goes to 0. So therefore, since the limit of 0 goes to 0 and the limit of 1 over 3 to the n goes to 0, and since our function here, cosine squared of n over 3 to the n, lies between the two, then therefore we can confidently say that the limit of that sequence is also 0. And that's from the sandwich theorem, also known as the squeeze theorem. This theorem says that if we have a sequence a sub n, if the limit of the sum of the absolute, that would be series. If the limit of the absolute value terms of the terms go to 0, then the limit of the terms in the sequence must go to 0. Okay, so basically what we could do here, let's say if we wanted to show that this alternating sequence here, show that it goes to 0. Well, first of all, if you took the absolute value of this, then basically what that would do is that would just remove this, because now whether this is -1 or 1, if you take the absolute value of it, it's just going to be 1. So this sequence would just be 1 over n. And so we know the limit of 1 over n as n goes to infinity goes to 0. Okay, so basically what did I show? I showed that the limit of the absolute value of this sequence goes to 0. So by that theorem up there, then the original limit must also, the original sequence must also converge to 0 as n goes to infinity. Now, a sequence is said to be monotonic if successive terms are not decreasing. So if the second term is greater than or equal to the first term, the third term is greater than or equal to the second term, and so on. All right. Or non-increasing. So maybe the second term is less than or equal to the first term, the third term is less than or equal to the second term, and so forth. Okay. Now, a sequence is said to be bounded if there is a positive real number m such that the absolute value of the kth term is always less than or equal to m for every k. So that's what we mean by a bounded sequence. It just means that the absolute value of every term are going to be less than or equal to some positive real number. That's all it means. If that's the case, then it's bounded. Okay, now this sequence is monotonic because, 1/2 and then 2/3 is, let's see, 0.5, 2/3. Okay, so 2/3 is actually greater than 1/2, 3/4 is greater than 2/3, 4/5 is greater than 3/4, and so on. So this is a monotonic sequence. Okay, but it is bounded as well because the limit as n goes to infinity of the nth term is 1. Because if you think about this right here, if you took the limit of n over n plus 1 as n goes to infinity, it's going to equal 1. So it's bounded above by the value 1. Okay? All right? So any number less than 1 would not be a bound. Okay? So anyway, that's what we mean by monotonic and bounded. Now, a bounded monotonic infinite sequence has a limit. So this sequence up here has a limit, and actually the limit is 1. Okay. So here we're just going to define the terms upper bound and least upper bound. So if S is a set of real numbers, then a real number U is actually an upper bound of the set if all of the values in the set are less than or equal to U. But a number V, this number V, is called the least upper bound of S if V is an upper bound. In other words, if V is an upper bound, that is, all of the values in the set are less than or equal to V. But it also has the condition that no number less than V is an upper bound. Okay? So in other words, if there's no number less than V that's an upper bound, then V is called the least upper bound. Now, so basically the completeness theorem says that if a non-empty set of real numbers has an upper bound, then it must have a least upper bound. Okay? So to illustrate this point, we know the sequence n over n plus 1 has an upper bound of 1. Therefore, it must have a least upper bound and limit. And that's actually, 1 is actually going to be the least upper bound as well. So hence the sequence converges. All right, that's pretty much it on the lecture on sequences. In the next section, we're going to talk about infinite series.